Okay, so let's resume our morning session. This is the last talk of this morning session, and it's my great pleasure to introduce Urna Basu. She did her PhD at the Saha Institute of Nuclear Physics in Calcutta, 2013, and she had postdocs in Leuven, CISA in Italy, and Paris South. And since 2018, she's associate professor at Underrepresented Raman Research Institute. And her work is on non-equilibrium systems, especially fluctuation and response in such systems. And today she's going to talk about activity-driven energy transport. So please go ahead.
Thank you. So I'd like to start by thanking Sumati and the other organizers for giving me the opportunity to speak at this very interesting meeting. So currently I'm in Kolkata. I moved from RRI like 5 years back. So I'm going to talk about activity-driven energy transport, which is a very different topic than what we have heard so far in this meeting. So I'll define these terms as I go along. Please stop me whenever you feel something is not clear. Okay, so I'll start from very basics. So we are all familiar with the concept of equilibrium. Equilibrium refers to the internal state of one system or relation among several systems. So when we say one system is in equilibrium, what we mean is that it's in thermal equilibrium. So there is no net heat flow through the system. It's also in mechanical equilibrium. So there is no net mechanical force on the system. And it's in chemical equilibrium, no net change in concentration of different components. It consists of different components, and no net exchange of matter. So this we are all familiar with from probably our basic courses. So essentially what equilibrium means is that there is no current flowing through the system, either energy, thermal, particle, probability, no kind of current is flowing through the system. So equilibrium systems are more or less well understood. So from a thermodynamic point of view, they are described in terms of few macroscopic variables like pressure, volume, temperature, chemical potential, etc. They are also kind of understood from a statmic point of view, from a microscopic point of view, in terms of Boltzmann-Gibbs theory. Things become more difficult, also more interesting when we go out of the realm of equilibrium. So whenever one or more of the conditions of equilibrium are violated, we end up with non-equilibrium systems. Typically, they carry some kind of current. It can be probability current, it can be energy current. And also these non-equilibrium systems are ubiquitous. Whatever we see around us, most of the processes are non-equilibrium, like cell movements within our body to wind threads around the earth. These are all non-equilibrium processes. Unlike equilibrium, there is no general theoretical formalism to describe this kind of process. Okay? So no thermodynamic description, we don't know how to, or whether it's even possible to describe these systems in terms of some macroscopic variables like pressure, temperature, etc. Most of the times these are also not defined in non-equilibrium systems. So theoretical approach kind of have to be system specific, condition specific. Sometimes we can only use models for certain specific phenomenon to sort of try to derive a general picture. So, so what we are going to do in this talk is to talk about one particular non-equilibrium phenomenon, which is energy transport. So when we talk about energy transport, the picture that we have typically in mind is like a system which is connected to two different, let's say, thermal baths, one hotter, one colder. So when we close the door to this room, so this room is kind of warmer compared to the outside environment. And if we look at the wall, so there should be a heat flow through the wall. So that's the kind of picture we have in mind when we talk about energy transport. So typically, what is considered is that this hotter body or warm, colder body, these are in equilibrium. So we have a unique temperature. So we have kind of a uniform temperature in this room. That's a warmer temperature. Also outside there is ambient temperature. So this is also kind of understood from an empirical and also kind of statmic point of view. There's Surya law, which says that the current for small temperature differences, it's proportional to the temperature difference, etc. So the question we are going to ask is at a different level. We are going to ask what happens if these baths are not in equilibrium. If the baths themselves are out of equilibrium, then of course we also have to figure out how to describe the baths because these are non-equilibrium systems, there is no temperature, at least, I mean, most cases one cannot define temperatures. So that's what we are going to, I mean, we'll try with a simple model in this talk. So this is going to be the outline. I'll give a brief overview of energy transport in thermally driven model systems, modeled by harmonic chain. Then I'll go to a model of active reservoir. I'll define what I mean by active reservoir. And then we'll see how this violates something called fluctuation dissipation theorem. And then we'll go to activity driven harmonic chain, and let's see how far we can go. Please stop me at any point if something is not clear. Okay. So let's start with energy transport in 1D. 1D is the simplest case one can think of. And let's consider a theoretical model. So our system, it's an extended system. It's modeled by a chain of harmonic oscillators. It's a very simple one because it's a linear system. So we can do things, we can calculate things explicitly. And this is driven by two thermal baths. So we'll first see what happens with thermal bath. And the kind of questions that are asked is, what is the current flowing through the system? Can one derive Fourier law? Can one define a local temperature? Can one calculate velocity or position fluctuations? So this started long back in 1960s with a paradigmatic example of harmonic chain connected to Langevin baths. This was done by Ryder, Lebowitz, and Lieb. Let me just give a brief review of that model. So here is a little more detail. So we have two baths of temperature T1 and Tn. T1 is larger than Tn, let's say. And we have n particles connected with harmonic oscillators. So I mean, these are two particles connected with a spring. So we know how to write the equations of motion, etc. And these baths are, these baths exert some force on the boundary particles. And these force typically have two terms. One is the thermal noise, that's the proportional to temperature square root of temperature, and also dissipation. So these two kind of balance each other and leads to something called fluctuation dissipation theorem, which is necessary for the bath to be in equilibrium. So if we model these two terms, they have to be related in a certain way. So we'll see this. So this is my explicit model. So we have these particles whose displacements are, I denote by xi, ith particle xi. So the first particle is connected to the bath. So this particle has this extra forces. This is a dissipation. Energy dissipated to the bath. This is a random force from the bath to the particle. Similarly, at the other end, we have similar force. So suppose I did not have this bath here, then this is designed in a way so that the whole system would relax to an equilibrium at temperature T1. Now that we have two different temperatures, it's going to be non-equilibrium. There will be a stationary state, a current will flow through the system. And for this simple case, this current was calculated exactly in this paper, and also later a different method was derived by Abhishek Dhar to compute the same result. So you don't need to remember the detail of this thing, but what is important is that this current is proportional to the temperature difference. So this is in the limit of when the chain is very large, we have an really extended system, but the current is proportional to the temperature difference. And if we look at local temperature in the bulk, then this is uniform. It's just the average of the two baths, right? T1 plus Tn by 2. So the oscillators in the chain are kind of at an equilibrium at a temperature which is just the average temperature of the two baths, and there is a current flowing through the system. Because these noises are, okay, these noises are Gaussian. Yeah, I forgot to tell that. Thank you, Sumati. So this, these connections are harmonic, so the equations of motion are linear, and these noises are Gaussian. So that's what allows exact solution of this system. And so one can go a little bit farther, and instead of taking this simple model, this Langevin bath, where the bath action is just this simple two terms, one can also use a microscopic model for the bath. So we can consider that the bath itself is consisting of a large chain. And then again, if this chain is harmonic and the noises are Gaussian, we can write an effective equation for the system, where now we end up with a dissipation kernel. Instead of a constant dissipation, I have a kernel gamma t minus s. So the acceleration of this particle depends on the history of velocity, and we have a noise kernel. This noise kernel is still Gaussian. This friction kernel can also be derived, but what is important is that because this bath is still in equilibrium, so it must satisfy fluctuation dissipation theorem. So the noise kernel must be related to the friction kernel through temperature. They are proportional. The proportionality constant is just temperature. These are in frequency space. I mean, again, you don't need to remember all the details. Only thing is that noise kernel and friction kernels are proportional. The proportionality constant is temperature. Once again, the current is proportional to the temperature difference of this extended baths. Now we are going to the main question that we are talking about here. So what happens when these reservoirs are away from equilibrium? Again, away from equilibrium can be modeled in a various plethora of ways. We are going to look at a particular kind of non-equilibrium reservoirs, the so-called active reservoirs. So what I mean by active medium, active reservoir is these are a collection of the so-called active particles. These are particles which self-propel themselves, okay? Like bacterium or birds, etc. So these particles, they do not have a global drive. They sort of drive themselves by consuming energy from the environment. Like bacteria, they eat food from the medium they are in, and then they make, convert it into motion. And these motions are typically persistent, so they sort of remember for some time their orientation. So that's a persistence which is a measure of the non-equilibrium. So this is not like an external drive which if you make it vanish, then it becomes equilibrium. No, these systems are inherently non-equilibrium. And examples start from bacteria to fish. So this is over a long time scale, length scales. Much smaller compared to the universal scales, but still, like this is typically 1 or 2 microns long to birds which are like centimeters long. Recently, there are also many experiments where these kind of motions have been mimicked with genus particles or micro and nano swimmers. So nowadays, people can really emulate this motion in a very controlled way. So it has also been investigated like a probe particle, if these are a probe particle is immersed in such an active medium where all the particles are these active particles, they are doing self-propulsion. So then certain kind of intriguing features are observed, like emergence of memory, modification of equipartition theorem, negative friction, which are absent in equilibrium medium. Okay. So we are going to talk about what happens if we connect an extended system with 2 such active reservoirs. So this is kind of a schematic diagram. So we have one active bath with a certain kind of, certain value of persistence to one system connected to 2 active baths with different persistence. So then we expect a kind of drive because the persistence are different, and we are going to ask what happens, what kind of current flows through this system. This is a schematic diagram. So now we come to a more explicit picture. So this is the system that we are going to talk about through the next half an hour. So this is my system through which we talk about the transport. This is a passive chain, same as what was considered earlier. What is different is that these baths now consist of active particles. So each of these particles, these red and blue particles, they are active particles. They have their own self-propulsion mechanism and self-propulsion time. Persistence time, which is different in the 2 baths. So this will be our measure of activity. And this is a conducting system, and we are going to see what happens. So these are our objectives. So first, we need to characterize the active reservoir itself, because it's not known how to do that, right? It's not defined by one temperature or one dissipation kernel. So we have to do it for a specific example system, and then we are going to talk about the non-equilibrium stationary state of the system, which is my middle chain, and the current and other kind of correlations that emerge. So this is my model. Now let's come down to brass tacks. So we have this is our active chain. This is the bath. So first one, this is given in terms of some m by m matrix. Again, you don't need to remember all these details, but finally, what we end up with is an equation, an effective equation for the probe particle, where we have a dissipation kernel gamma. Dissipation kernel gamma and a noise kernel. So what we expect is that the activity has somehow modified these kernels. No, it depends. So each particle has its own noise, but there is no explicit space dependence. They are independent. That's the first thing we can do. L is the index of the particle. That can be different, but there is no explicit space dependence. I mean, so I have F1, F2, F3, these are identical processes. So for a given chain, they have same persistence time, but at any time, they're not same. I mean, F1 and F2, the value of F1 and F2 can be different, but there is no explicit space dependence that is given. These are just stochastic processes. Yes. No, so these are, so F itself is a sum of white noise? No. So it's particularly not white noise because we want to model an active system. So if these were white noise, we would end up with the passive system with a given temperature. White noise doesn't have any other information, right? It's just a strength of the noise. So these are not white noise, these are some colored noise, okay? And this tau is the persistence time of that colored noise, okay? Typically, these turn out to be exponential functions, but we can also do, I mean, other gamma functions, etc. Okay. Only thing is that there is a time scale. So white noise doesn't have a time scale. This is 0. Here we have a time scale tau. That is the measure of the activity. That is going to sort of define in the end. I mean, how much current is going to flow through my extended system. Okay. So for now, we have one parameter tau, which is characterizing my active particles, my active bath, and we end up with a dissipation kernel and a noise kernel. So let's look at this term in some more detail. So the dissipation kernel can be calculated exactly. It's given in terms of some Bessel functions. Again, you don't need to remember the exact form, but look at this form. There is no information about activity here. There is no tau here. Okay. So this contains only the information about the chain, the structure of the chain. So this shows a t to the power minus half decay at late time. But this is only chain structure. So this is same for the passive bath as well as in active bath. So what contains the signature of activity is the noise kernel. But okay, let me just say one more thing about the dissipation kernel. So we can also calculate the spectral function, the function in the frequency space, and compute the asymptotic behavior for small and large omega. It goes as 1 by square root omega for small omega, but these are all again same for passive bath as well, as long as this is linear and I mean just nearest neighbor connection. Now we come to the effective noise, and that is very important. That's the crucial factor. So now if we calculate this noise-noise correlation, remember for the white noise, this G tilde function is just temperature. There is no other information there, but now we have a specific frequency dependent function which contains this noise-noise correlation. This H tilde is the Fourier transform of this function. I have not specified this function yet. So far we are keeping it completely general, but there is H tilde, which is the Fourier transform of the noise-noise correlation that is appearing in this function. Again, compare it with the white noise case that we had. We simply had T here, which is replaced by this H tilde omega function for this case. So that is the effect of activity, having the activity in the system. Okay. Now let's take a specific example. So what we consider is the so-called run-and-tumble process. If some of you are familiar with the term, if you're not, I mean, it doesn't matter. It's basically what it says is that this is like a persistent random walker. It has a memory. So it has a particular direction, and the direction flips with a constant rate. So the inverse of that rate gives a time scale up to which the random walker remembers its orientation. Okay. And if this is again very simple, we can compute everything. So it turns out that this H function is simply exponential. It's just a dichotomous process. The H function is simply exponential, and the frequency spectrum, which is the Fourier transform of this, just pure Lorentzian. Okay, but it depends on omega, unlike the passive case. So we took a particular example, but other known kind of active process can also be done. If some of you are familiar with these words, I mean, these are all equivalent. It can be done. H function is a 2-point function. Yeah, ft prime. Tau is the so yeah. So, sure. So this was this t minus t prime by tau. Okay. So ft prime is basically e to the power minus mod t minus t prime by tau. That's the scale up to which the memory is remembered. Yes. So let's look at this noise correlation, this G tilde function. So this is something like this. I mean, these are for different values of I think tau. This is how it depends on omega. And this is my gamma tilde omega. This again, remember, is same for passive and active both, but this is the kernel which makes it different. One more thing is that suppose we look at tau going to zero limit for very small tau, then we kind of expect that this will be equivalent to a passive system, and it indeed is. Then H tilde omega is proportional to tau. So for small tau, this V square tau kind of acts like a temperature. That's what we also expect, because if the memory is short, we sort of expect that it would converge to a passive kind of system. Okay, so mathematically it can also be shown. So now we come to the main question. So now we are ready to tackle it. So we have an extended system. This is my passive chain. We connect one such active chain to one end, the other one to the other end. So tau 1 and tau n, these are different. So this is now my drive. So two active chains, one with persistence time tau 1, the other one with persistence time tau n. These are different, and we are going to ask what kind of current is flowing through the system. So we can now write the equations of motion, the Langevin kind of equations of motion for the passive particles, and we simply replace the previous thing by new noise dissipation and noise kernels for the first particle and the last particles. The middle particles are not directly affected by the baths, so these equations remain invariant. But of course, because they are interacting with their neighbors, eventually they are going to feel the effect of the bath. So here we are going to ask, look at local velocity fluctuations, temperature profile, correlations, and current. These are the main observables. So once again, the system is linear. We can solve it explicitly. I'll not go into the details of the solution, but let's first look at the temperature profile. So what do I mean by temperature profile? In equilibrium, temperature is given by average of velocity fluctuation, V square average. So we define a quantity like that and ask that how does it behave. Okay, it's not really temperature in the sense that there are other equivalent definitions of temperature in equilibrium. It might not be same with that, but let's just call it some temperature like quantity, and let's plot it for the chain. So it turns out that this quantity is also uniform in the bulk, very similar to the equilibrium bath driven chain. In the bulk, it's something it has a uniform value except at the boundaries. Okay. So far we haven't seen any difference with passive driven chains. So next we come at typical velocity fluctuations, which again are Gaussian for equilibrium systems. Here also we see a Gaussian profile. So far it looks like, what's the big deal with active reservoirs? But now if we look at correlations, now we look at 2-point correlations of velocity. So VL prime, velocity of two oscillators which are separate from each other, and how are they correlated? So in equilibrium, this is simply proportional to delta LL prime. So oscillators are not correlated, their velocities are not correlated at all. But here what we find is that now a finite correlation length is emerging due to the activity. Okay? So this correlation function can be computed explicitly. What is important, it's a sum of two exponentials, okay, with length scales L1 and L2, and these length scales are proportional to tau 1 and tau 2. So we have one length scale coming from left reservoir, another length scale coming from right reservoir, and of course which one is longer is basically dominating the decay of the correlation. So this is our first clue that activity drive is really doing something different to the system. Okay, it's generating a finite correlation length. The velocities are being correlated over a distance which is proportional to the larger activity. Okay, we can also look at temporal correlation. Once again, we can compute it. You don't need to remember the exact forms, but this is also different than in the passive case. So particularly at short times, these oscillations are emerging, which are different than, there are also oscillations in the passive case, but the actual form is different. And okay, so correlations, 2-point correlations in both space and time, they sort of retain the information about activity. Okay. And now we come to the final question, what is the current flowing through the system? Okay. So our chain is a passive chain, so there is no other injection of energy or dissipation in the chain. Only thing that comes is through the boundary. So there is a constant current flowing through the system, and This also we can calculate explicitly. And it turns out that this, what I call active current, this active current is given by a form which is Landauer like, but in the Landauer case, this is simply, in the passive case for which Landauer derived his formula, this was simply T1 minus Tn. Okay, this was simply the difference of the temperatures. Now we have a complicated omega dependent function, and that we have to integrate over omega. So now we have a different kind of behavior of the current, which is dependent on the activities of the both reservoirs through this function. So this integral cannot be done explicitly, but we can numerically evaluate it. So let's do that. Let's see what happens. Okay, so this is a plot of this active current for, as a function of tau 1. So the activity of the left reservoir for different values of tau n. And now we see something very intriguing. We see a non-monotonic function. Okay, let's follow one curve. Let's take this gray squares. So this is for tau n equal to 1.5. I'm varying my tau 1. So it starts from some negative value. Tau 1 is smaller than tau n. So there's a negative current flowing through the system. So it goes up, up, up. At 1.5, the two activities of the two reservoirs are same. So there is no current. The current crosses 0. Then it goes up. But as we increase tau 1, it again starts to decrease. Okay. What is more is that at some point, it again becomes negative. So there is a reversal of current. So we are increasing the difference in activities of the two reservoirs. So the current is first increasing and then decreasing. Okay. So this is something very counterintuitive. This is something we never see in equilibrium processes. Okay. Not only equilibrium processes, but also systems driven by equilibrium baths. It can never happen that the current reverses its direction. So there are two features here. One is that they show this, what is called negative differential conductivity. So the conductivity becomes negative, goes down with the increasing gradient of activities, and it also becomes negative. So there is a direction reversal. So these are two things which are specific to this activity driven system. We don't see this for temperature driven systems. So so this is exactly what I mentioned. So these are two features, negative differential conductivity. Negative differential conductivity simply means that if we look at the slope, dj, d tau at some particular value, then it becomes negative for a certain range of delta tau. And then this reversal happens at, so we have current reversal at 2 points. Once when tau 1 is equal to tau n, that is expected because then we change the direction of the drive. Of course, the current is going to reverse. But there is a non-trivial point, which is a function of some tau 1 star, which is a function of tau n but not equal to tau n. There is a current reversal. Okay. So how to understand that? That is a question. So let's first look at this negative differential conductivity in a little bit of overview. So this kind of negative differential conductivity has been observed in some other non-equilibrium systems with where there are presence of obstacles, kinetic constants, models of models with rotor chains, etc. But these are all very strongly nonlinear systems, and there also it's kind of understood how this negative differential conductivity comes about. So this is long list of papers which have looked at this negative differential conductivity. But what is more sort of surprising here is that here we are dealing with a completely linear system. Okay, this kind of reasoning that worked in these systems with obstacles or rotor chains, that does not apply here. This is a completely linear system. Here the only reason behind this negative slope is this activity drive, this active drive. So the question next is, of course, what is the physical origin? Can we say something about, like in thermodynamics, we have this gradient sort of description. So if the, can we describe this drive in terms of some gradient of some observable or some variable? So we don't have a very good understanding of that. We understand this sign change mathematically. The best we can do for now is that let's look at this frequency spectrum. So this is the Lorentzian frequency spectrum we have. This is not Lorentzian, this is G tilde, the full thing. H tilde times the gamma omega. So this is one function. And then we have to take its convolution with this function. And it turns out that that is a non-monotonic function of tau. Okay, this is kind of a mathematical description, technical, but physically, how to understand this is kind of, so each reservoir has its own band. Okay, this Lorentzian gives sort of a width around omega equal to 0. So each reservoir has its own band, and then how much current it's trying to flow, drive through the system depends on the overlap of that band with the system's frequency band, so which is around square root of k by m. And then whichever reservoir sort of wins, which has more overlap with the system, that decides in which direction the current would go. This is not very satisfactory, I accept, but we don't know how to do better. If you have any idea, that would be great. So for now, what we ended up with is that we have an activity-driven system, okay? And we looked at, we started with an active bath. We tried to characterize it by computing the noise and dissipation kernels. It's a very simple model, it's a linear model. And so that's why we could compute things. And then we looked at the current flowing through the system. And it turns out that due to the active nature of the drive, there are certain features which are never seen in equilibrium. It's like the current changes direction at some non-trivial point. And also the non-equilibrium stationary state now becomes, correlated. The velocities are correlated. Velocities at different times are also correlated. And transport properties show some weird features, let's say. So there are many open questions in this direction. So as I said, what decides the direction of the current? Is it possible to have some sort of thermodynamic understanding to that? Can we understand this as a gradient function of something, some kind of thermodynamic force, let's say? Another question is, do these features, we looked at only a one-dimensional chain. So what happens if we consider this in higher dimension? Is it possible that still this current reversal, etc., that survive? So this we have not looked at yet. What is the effect of disorder? So in equilibrium systems, or at least equilibrium driven systems, we know that disorder has some drastic effects as regards to system size dependence, etc. So what happens for this case? This is another open question. What happens if we don't take just a linear chain, but also like some FPUT chain where there are nonlinearity? So this we have looked at with numerical simulations. We cannot do much analytically in nonlinear chain, but it turns out that at least from numerical evidence, what we see is that both this NDC and direction reversal, they actually survive even when there is anharmonicity. We cannot calculate the current explicitly, but they seem to survive. And also for the anharmonic case, now suppose we have a drive which has a thermal component to it plus activity. Okay. In the linear case, we can show that these two sort of decouple. So there is one current which is proportional to the temperature difference, and active current, which is what we discussed. But if we have a nonlinear system, it's not so easy to decouple these. So now we expect that the thermal current and active currents are sort of, they would couple with each other. So we also want to look at the, conductivity matrix somehow. What is the cross terms in that matrix? So these are the open questions, and let me end by thanking my collaborators, Ritik Sarkar, who is a PhD student in my group at Kolkata. Ayon used to be a student at RRI. He's a postdoc now at Leuven, Belgium. So yeah, if you have any questions, I have 10 minutes left.
Okay, thank you for this very nice talk. Questions? Sylvie and then Dimitri.
Thank you. Thank you for your presentation. I'm outside the topic, so I'm going to ask a naive question. The fact that you have a noise introduces singularities, doesn't it, in the solution, in solving the equation?
Noise, singularity in what sense?
Well, noise is singular, for me, is a singular object. So maybe we're not talking about the same noise.
Probably not. Because
what kind of noise? I haven't quite understood what kind of noise.
So this you can think of, so suppose when we talk about a probe particle in a bath, okay, so the bath typically has a much faster time scale. So suppose you have a bigger colloidal particle, a bigger colloidal, like a cork immersed in water. So the water particles are much smaller, they're much faster. So they basically impart force on this bigger particle, which are much faster. Okay, so these are approximated by a Gaussian noise. It means that there is no correlation. I mean, the force that the bigger particle feels at one time.
Gaussian noise is singular.
Singular in what sense?
You can't differentiate.
Oh, that's fine. That's fine, because we don't need to differentiate it. All we need is to
But
integrate
when
it.
you doesn't it give rise to singular integral kernels when you solve your equations? No?
No. So not in.
I'm thinking of stochastic.
At least, I mean, the kind of quantities that we look at. So these all end up being. So if you look at, okay, I didn't. So this is the solution. This is the structure of the solution. So if we have a Gaussian noise here, all we need is the integral, and this 2-point correlation is fine, right? It's a delta function. And finally, we end up with a finite quantity. So what we need to be careful about is what you mentioned, of course, that Gaussian noise is singular in a sense that, okay, so when we integrate these equations, we cannot use Eulerian methods. So we have to remember there is a square root delta t additional factor. So does it make sense?
Factor? What's this?
No. So what I mean is that suppose I have a Brownian particle, which is this, right? So when I integrate this over a time delta t, so this is the effect of this Gaussian noise. I mean, it's not Eulerian, it's not.
So you're discretizing.
When I discretize, yeah. That
So
you have to be careful
you're
about.
introducing.
It's effective, yeah.
Okay.
But I mean, the kind of quantities that we look at, Gaussian noise is the simplest, and it doesn't give rise to any singularity per se. But maybe for some other observables, yes.
So how would you model this kind of energy transfer in higher dimensions? Here you use the chain of harmonic oscillator.
Yes. So, I mean, one naive way would be to look at a network of oscillators in 2D, right? And one boundary, all of them are connected to a particular kind of bath, right? So we can have, I mean, that's the most naive way one can think of. So we have, our system would be 2D. And then this will also be a network of active oscillators in 2D. Okay, that would be the most simple way to do that. But okay, I mean, we have not done it, so we don't know whether it works or not, or what it gives.
A very naive question. So you mentioned occurrence of memory.
Mm-hmm.
So does this mean periodicity of some phenomena?
No. So this basically, in this context, what it means is that suppose you think of the motion of a bacterium. So what it does is that it moves with a constant speed. It moves with this constant velocity for some time, and then it suddenly changes its direction. Okay, the memory means that how long it remembers that it was moving in that particular direction. Okay, unlike random walks, ordinary random walks, what it does is that, or Brownian motion, what it does is that at each instant of time, I mean, doesn't matter how small you go, at each instant of time, it chooses a new velocity, new direction, etc. So here, this is persistent random walk. I mean, in the discrete sense, it's a persistent random walk. It just remembers in which direction it was moving for a certain time before changing. So that's all I mean. Yeah.
Okay, yeah, I see two at the same time. I don't know who's first.
Yeah, I have a naive question. This current which you plotted as a function of tau 1
Mm-hmm.
and for a fixed tau n.
Fixed tau n, yeah. Just 1 second, yeah.
So you can also do the other way around, right?
Sure,
You can fix
yeah.
that. And can you reconstruct J as a function of difference between tau n and tau 1?
No,
Will it give
it's
you
not.
something?
It's not a function, it's not a pure function of tau 1 minus tau n. So if you look at this equation, so you know that this G tilde functions are complex functions of, I mean, not very complex, but it's not linear in tau 1 and tau n. So only in the limit when tau is very small, then, so if you remember this thing here.
Then it becomes the temperature of the bath.
Yeah. So if you remember, so this was the function, okay? So when tau is very small, we can ignore this term here. So then it becomes proportional to tau. And in that limit, which is like the passive limit, then it becomes a function of tau 1 minus tau n. Otherwise, it's not.
Okay. So other thing is you had this living sides, both of them identical, right? M connected pieces and M connected pieces.
Yeah.
You could have made it different, and will it help you to get understanding on this negative current?
Just 1 second. You mean
Yeah. So
this one, right?
Yeah.
Yeah.
So this is symmetrical, no? The left active reservoir and right active reservoir.
Symmetric in the sense that, I mean, they have different, like tau 1 and tau n are different.
I agree.
Yeah.
Yeah, but the M of them which you are considering.
M I took same, yes, but on the other hand, we also took M to infinity because we want baths to be larger, right?
Okay.
So bath typically means that your system, whatever it's doing, it's not affecting the bath too much. So
it's
we
not
need the
finite M. So
it's. I mean, we did the calculation with finite M,
yeah.
and then we took M going to infinity, but it would not matter too much.
So the puzzle still remains. Why the negative?
Yeah. I mean, in a physical sense, it does remain. We don't know.
I have technical question. When you said about the diffusion, sorry, I have technical question. And when you said about the fluctuation dissipation theory, you assume that they are proportional to exponential functions. So I don't remember.
When?
which- Go.
Here?
No.
Later.
Where was the H function?
Okay.
function.
Later, yeah.
Okay, my question is it related with the telegraphic equation? With telegraphic
Telegraph equation. Yeah. So this process is
Yes.
exactly a telegraph process.
Okay.
This is, but I mean, whatever we have done is not, restricted to telegraph process, right? There are other processes which also give rise to this exponential function. So it holds for all of them.
So only you assume that the dichotomic noise
Mhm.
and which
No.
fluctuation dissipation theory it's
No.
relative.
So let me. I mean, this is a two-part question, I guess. So first thing is that this is an example. Okay. So this is one example of dichotomous. I mean, the example is dichotomous noise, which gives rise to this exponential function. But had it been something else, suppose I have a 3-state process. Okay. Or there is something called clock model where this function is a gamma function. Okay. Even then, all our calculations hold. Qualitatively, we see exactly the same thing. So that's the answer to one part of your question. And the other part was FDT, right? So FDT is violated by, So FDT is violated as long as this function is here. As long as we have a frequency dependent spectral function, FDT is violated. So ordinary FDT means, okay, violated, I mean, it's violated in a specific way so that we also know this proportionality function in some sense, right? Does it answer your question? Or?
Yeah. Thank you.
So depending on what kind of noise we take, we'll end up with a different function here. All of them will violate FDT unless this is a constant.
Okay, I don't see any more questions, so it's time to thank our speaker again and all the morning session speakers as well. Thank you.